And now, for those of you who joined, now we are in the first edition of the Africa webinar. We want to showcase, solutions for polyurethane and engineering plastic solutions. Now it's the final presentation in our webinar. This event is broadcast in Portuguese and in English as well. So we have an outreach for the African countries and other countries as well. And then at 2 p.m., we're going to have another edition of the Latin American webinar. That's the kind of event that we have been holding for so many years, right? So in addition to allowing you to get to know innovations and new technologies, we would like to publicize the trade show and the International Congress on Composites, Polyurethane, Engineering Plastic and Thermoplastic Compounds in its 11th edition, FEIPLAR FEIPUR, from August 16th to 18th in São Paulo Expo, here in São Paulo, here in Brazil. So I count on you. You're all invited. You're going to be dearly welcome. And now to close this Africa webinar with one of our best experts in the market, Dr. Francisco Carvalho, the director of IBCOM. He's going to talk about production strategies. So get to know the applications. Good morning, Francisco. Good morning. Good afternoon to everybody as well. Here we are. I am Francisco Carvalho, and thanks to Simone. Simone is the strategy person for the composites, right? So IBCOM is a group of professionals from the composite area. So we develop products, processes, technology. We do structural calculations as well. We provide training to corporations. And we provide advisory services as well. We'll be participating at FEIPLAR as well. We're going to have a session at FEIPLAR on the durability of composites to be introduced by Dr. Antonio Carvalho. It's a quite new topic, right? It's unheard of all around the world. Speaking not only about durability, but also rupture statuses and the behavior of composites. We are going to be addressing it very comprehensively. So let's go to the next slide. So we'll try to cover our experience in process and product development for composites, trying to be as competitive as possible and trying to equalize quality and cost. So this is what this presentation is about. Next. Well, in order to, offer a competitive product in the market, there must be some important assumptions that must be taken into account. First, structural dimensioning, structural calculation. So we have to work in accordance with the standards in terms of safety coefficients, for example. So we have to work precisely and efficiently. For example, if we are to use, or for example, if we do not take into account the safety coefficients, we may run into failures of the product. And then if we exceed and if we use too much material for the sake of safety, we are not competitive. We may not be competitive in the marketplace. So the next step, it is the previous slide actually. So we have to think about the production process. If we are to produce in large scale, for example, first we have to organize our production process according to the market demand. We don't want to have losses, right? We don't want to waste our investments. We don't want to see any delays in the processes. So the dimensioning of the production process is very much important. And then the choice of raw materials. We have to use the most appropriate raw materials. For example, raw materials with added value. Whenever we can use continuous roving, that is the simplest way of using fiberglass, it's going to be better, right? Because the fabrics, the mats, they have their added value. So if we can use, a raw material that has a lower added value, that's okay. Next. Composites, and the major advantage of composites, and it's fantastic, right? It has to do with the engineering design. When we worked with the metals, the isotropic materials, for example, steel has a single elasticity modulus. You have to work with that elasticity modulus. If you want to develop a product made of steel, you have to work with that. And you must find the right thickness so that the required properties are met by that elasticity modulus. Well, composites are anisotropic. They may have, different properties in different directions within the part. And the strategy is that you can place your filler where it is most needed, where the strains happen. So this really facilitates the life of the designers. And with the blends and the mixes, you can also formulate a material with the properties that you require. So you have different kinds of reinforcements with different kinds of properties. And the matrices, they could be polymeric or metal matrices as well. And you can formulate a material with the required properties. Well, we can boast about this fact. So you tell me what is the thickness that you require, and we can manage to formulate. We manage to formulate a material to get there to the required thickness. I'm exaggerating here, but this can be done. And thanks to the anisotropic qualities of the composites, thanks to that, we have a wide array of possibilities. Next. This is just an illustration of what I said before. You have the matrices. The resins, metals, elastomers. And by using fillers and reinforcements, you can place the fibers in whichever direction is needed. You have chopped fibers, you have continuous fibers. So these are the ingredients that we have in hand to formulate materials according to the design. We can formulate the composite materials. Next. So I'll cover this briefly because you know this. Here we show the anisotropic characteristic. You have continuous roving, and then you have the strength along the length of the roving. So you can position anywhere. You can position it as you like. Fabrics, we have the fibers in all of the directions. You may have fibers at 90, at 45 degrees, depending on the fabric. So we have fabric manufacturers that can do it in any direction that is required. So they can, truly organize the material as needed. Next. Chopped fibers, and then we develop and produce the mats. Chopped fibers, well, in this case, it's virtually isotropic material because it produces, the same properties in all directions. This really helps us if you need to be more isotropic in your product. Next. Here we can see the wide array of possibility in using the fillers, the wide array of anisotropic arrangements that can be done in the product. Next. Let us talk about the structural project. So this is widely used in electrical networks. You see the truck with the crane that elevates the operators. So one of the characteristics of the arm is electrical insulation. So this characteristic is required. So there is the metal part, that is the activation part of the device. And we have the white part that is made of composite. Polyester with fiberglass to make sure that it can be operated. But in order to make it work, there must be a certain mechanical stiffness, there must be the right strength. So the cross-section of the beam, it's a rectangular cross-section. You have the height of the beam, and the stiffness module of this beam is the elasticity modulus times the inertia moment. And the inertia moment has to do with geometry. It depends on the height of the beam to the cube, times the weight, and then you have the formula divided by 12. If this dimensional factor is fixed, all you can change is the elasticity modulus. So how can you get the elasticity modulus right? You're going to use a material like fibers with the appropriate modulus that will serve the purpose, and then you are going to place it in the right direction because the modulus varies according to the angle of placement, the angle of positioning of the fibers. So we'll see that further down the road. So here we compare this material in terms of stiffness. I'm not talking about insulation. Well, if we compare, for example, steel and fiberglass and carbon fibers and aluminum. So that's what you see on the chart, the four materials. So in some cases, by designing it properly, we can see that the carbon fiber beam, you can see here that the carbon fiber beam has a performance that is a bit better. Well, the performance is similar to that of steel, but the price is not that high and the weight is much lower. So it's a much lighter piece. And then we have the comparison with the glass fiber. And then you can see that later in more detail. So you will have the opportunity of receiving the presentation later. Next. When we size the composites, in the case of poles and tanks and beams and pipings, the criteria that we use is the criteria of maximum deformity. So stiffness is based on the maximum allowed deformation. So we use elongation as a reference. So we use maximum elongation. I think you're all familiar with that in the Hooke law. And we use that law. Of course, we are not going to use rupture elongation because we are not interested in having a rupture of the piece. That's the death of the piece, right? For a piping, for a tank, for example, we can use elongation, the elongation that will not allow for exudation. Exudation is when liquid comes to the fore and we see the sweating, so to speak, of the piece. So when you have elongation, as you increase elongation, you have some fissures and cracks that may emerge. And then you further increase your elongation rate up until you rupture the piece. But we work at a level that is much far away from the rupture level. So you use elongation to deal with exudation, but rupture is, not an event that is related to such level of elongation. So we use the maximum stiffness criteria. That's the criteria that we use. So here we have an example on how this works. In the filament winding, if you are producing a cylindrical body, it could be a pipe, it could be a circular tank. So the direction of the fibers is important. So you do the roving at a certain angle. You do the winding at a certain angle. And then you can measure the mechanical strength, you can measure the modulus, both in Y and X directions. So considering from 0 to 90 degrees, here we can see the variation of the elasticity modulus. So we have X in the length direction at 0 degree, and the maximum is 400,000 kilos per square centimeters. That's the maximum, 400,000. And then in the Y direction, we have the other measurement, the MIB, the elasticity modulus. If you are producing a pole, well, the test for the pole is the flexural test. So there must be maximum strength along the length of that pole. So the elasticity modulus in the X direction, you have to reach the maximum in this case. So you're going to wind at an angle close to this. We work at 10 degrees in this case. By pultrusion, you can do it at 0 degrees. But then it's too expensive. Yeah, you have to produce the molds and everything else. If you are to produce a pipe, it's the other way around. Let's go to the next slide. So if you are to produce a tank, so we have internal pressure. So in this case, the purpose here is increasing diameter, right? So you use the modulus in the Y direction. It should be as high as possible. So you wind at 70, 75 degrees, about that.
Here you see the assay taking place in this post. It's attached to this foundation or this base, and there is a system pulling it upwards. So here we have, to check the maximum deflection, we have a specified load, and the arrow for the deflection cannot go above a specific threshold. Here the maximum angle is of 10 degrees. So 10 to 15 degrees. Some people go up to 20 degrees. But we're going to speak more about this in a minute. This is a video. If we could click on the video, please. Okay, now we see the image, and the fiber is at 10 degrees. So you see the winding. Just look how the arm deposits the fiber. This is a 3-programmable axis machine. Later on, let's watch the video again. Because at the end of the process, you have to anchor the fiber. But I'm going to give you more details in a minute about this. So the machinery needs these resources with two axes, it would be difficult to anchor the fiber and also to do the winding at 10 degrees. So this is our technology. It's manufactured by OMAC, which is our partner in producing the equipment. We also have Pultrogen equipment and several other options for the industry. This is a profile, and usually the main request for profile is inflection. So most fibers are in the length or in the axis direction. So you have continuous roving here, then you have a mat that provides resistance or improves resistance in the y-axis, and the surface veil to give this finishing on the surface. We are constantly working with the anisotropy of composites, which is a very interesting property of composites. In this slide, we speak about the market for composites. So we have performance, mechanical properties, costs. So from the lowest cost to the highest cost, and we also have yield or productivity. And different industries use it. So the aerospace industry, it needs high performance, which is the blue arrow. Regardless of the cost, usually aerospace parts are very expensive because it takes long time for production. There's a need for autoclave in order to reach productivity, and the yield is usually low. When we look at the mechanical industry, we do need good performance, of course. Costs are important, but they are not key. And productivity, same thing. Today, I am approaching what we call, or the yellow part, which is civil construction or the infrastructure industry, in which you manufacture posts, tanks, tubes, which we use for infrastructure and civil construction purposes. So we need low cost because we want to be competitive, of course, with traditional materials. Yield has to be high to meet the needs of the market. And I'm going to show you a couple of examples that we have, mostly in this industry, which is the one that is more trending now in developing countries such as Brazil, South American, African countries. There's a lot of use of composites in the civil construction industry. Well, criteria for structural dimensioning of composites. We've spoken a little bit about this. First, we need to do the structural calculations in order to establish mechanical properties. Currently, with the knowledge that we have in terms of composites, which we didn't before, we are capable of calculating the mechanical properties of composites. We can set up rigidity or stiffness matrices and get to know precisely the mechanical properties. And this is available in our books. I believe that all of you are very much familiar with this, so I'm not going to go into details here. Same thing, I have already mentioned this before. What is necessary to do the appropriate formulation of the material? Well, the appropriate structural dimensioning of the material, also the development of the productive process with the best possible technology. And there's something important here. In a minute, we will see that what we invest in technology to produce something means very little when compared to the final cost of the product. When you do need a lot of technology, it's usually maximum of 2% of the cost of the product. So when one decides to invest in production, we have to look for the quality of the equipment and not for price. If you buy machinery or equipment, you might buy something which is not that great, but you will regret it because you will lose on competitiveness and you will not be able to face the quality provided by your competitors. If your competitors do invest in technology, if your competitor invests in an appropriate production process. Well, now let's analyze these products with more attention. Let's start with these posts. These are complex because it's a conic-shaped beam, and the structural calculations are complex because the inertia moment or the geometric factor varies according to length. So the stiffness of the post can vary at each millimeter because there's a variation on the inertia moment. So the structural calculations are extremely complex. We solved this challenge recently. The world has solved this challenge recently, thanks to an IBCOM member, Professor Marmol, one of the most renowned structure calculists in Brazil, an incredible mathematician of world renown. He developed a formula to calculate the minimum thickness of the post. And because of that, we have developed a program for structural calculation for graduate schools, and several companies in Brazil and Latin America are now using this program of ours. Production is also complex. We have to work with a 10-degree winding angle, 10 to 15 degrees. Usually people work with 15. So for winding purposes, we have the edges in which we need to anchor the fiber. We need to program the equipment correctly in order to anchor the fiber without increasing too much the thickness in the edges of the post, because if you use too much material, you're wasting money. And if there is a variation in the geometry, you will also alter the rhythm or the pace of winding. Unavoidably, there will be an overlap in the fibers or in the fiber ribbons. Therefore, the production program must foresee all of this. the central part of the post, this is where we have geodesic winding. Here we have more effort or more tension, and here we must work at a low angle. In the part that is underground, this problem is not that big. But closer to where the load is applied, the problem is not that big either. That helps in anchoring without having to resort to other methods that might lead to a loss of material. So if you want to be competitive, you have to work with the best technology, with an equipment with at least 3 programmable axes to meet the requirements, which are very important. We do have this equipment, and we will show this to you in a minute. And you need yield. Posts are produced in huge amounts, of course. So we need production capacity. The more we produce, the lower the final cost. Here we have another video, if we can watch it. So this is a post-production machine. Here you see that it produces 2 posts at a time. Again, the 3 programmable axes, high productivity. And we have several of these machines currently working, successfully working, in Brazil and in South America as well. Yes, so looking at the video once again, the automatic system is important. The positioning of fibers has to be correct. So this equipment ensures that we produce at high quality and high productivity levels. Okay, now let's look into the cost of a post. Raw material, which is the purple slice, the cost of raw material represents over 40% of the total cost of the product. Then you have labor. Labor is quite decreased. The labor costs are quite decreased by the fully automated process. Then we have fixed costs for the industry. Since production times are short, fixed costs are very important. And they represent electricity, operational costs, rental or leases, all the expenses. So the longer it takes to produce, the higher the fixed costs. And the 1%, that's the cost of machinery and technology. It's almost equal to nothing. It's 1% of the cost of the post. And with just that, you can produce high-quality material at low cost, something that is highly competitive. It's really important to take this into account. So we really have to think about production. Regarding materials, we use roving. which has less added value. And we use the roving, and we focus on the main efforts, reaching excellent results. So, manufacturing of tanks. Brazil has several tank manufacturers used in the chemical industry, and now with the water and sanitation industry growing, we have many tanks for water treatment stations. And these tanks in the beginning, they were made with no technological foundation whatsoever. And they faced several problems in several places. I've seen tanks that had flaws because they were built with no criteria whatsoever. Besides being a problem to the composite market, companies face huge losses when this happens. They can even shut down. So we have to be very careful in tank manufacturing. We've developed programs for structural calculations that embed all the technology necessary to make these calculations. We've developed equipment, which I'm going to show in a minute. Tanks, these storage tanks, their main role is for hydrostatic pressure. You would rarely manufacture a tank of the kind for anything beyond atmospheric pressure. So usually they are dimensioned with this in mind. But there is a very important aspect that not a lot of people take into account, which is wind, the wind factor.
So ABNT, the Brazilian standards, they do have a table for winds. So depending on where this is going to be installed, you have to take into account the wind pressure. It has a big effect on the tanks, especially the highest ones. When you calculate, you have to take this into account. That's very much important. Next. So here we see the many possibilities addressing the cost of the tank. When you use, filament winding, so you use a low-cost raw material, that's the roving, and then you direct the production. I can't really see the figures, I don't know if you can see them, but it's 89%. 89% of raw materials. That's the cost of raw materials. It accounts for 89%. Labor, actually production means labor here. It dropped to 2%. Got better, right? Much better. And we have fixed costs, 8%, amounting to 8%. And equipment amortization and technology accounting for 1%. So that's the ideal cost of a tank. And they use filament winding to make it. So let's see the next slide. Using spray up. So you use chopped fiber in this case. It's virtually an isotropic material when you use chopped fiber. And the speed of production is quite good. In the case of spray up, we can even, produce by means of robots. We can use robotic systems to perform spray up. Quality is greatly improved because the distribution of fibers is very much uniform. So with a spray up, and then we'll see later the comparison, the costs of the raw material are the highest. Then we have labor and production costs, which is similar to that of filament winding. Next. Some people use manual molding, and then everything is reversed in this case. You can see here the raw material costs account for much less. The fixed costs are higher because it takes a long time to produce. And the raw material cost, we use high added value raw materials. I mean the fabrics and the mats. So people sometimes make mistakes in this case. So it's a very low competitive edge that we have in this case, that is using, manual molding with the fabric and mats. You can do much better with a filament winding or even a spray up, especially if the spray up method is based on a robotic system. Next. So here we see the results. So can we enlarge? Very good. Now it's better to see. So we see productivity. The larger bar is manual molding. Filament winding and spray up, they have a better productivity level. In terms of cost, when we use manual molding, both with mat and fabric, the cost is much lower. Filament winding, you can see, and spray up is more expensive than filament winding because the chopped roving has very high mechanical properties and the thickness is much greater. So we see this represented on the weight of the tanks. Manual molding, the weight is smaller than that of spray up, because in spray up we do have enhancement of the mechanical properties. Okay, next. That's a tank production machine, and that's a video. So it has a robotic arm. It's the most advanced machine that we have. This robotic arm is used to apply the chemical barrier. If you are to use any prime, it can, it can be applied by the robotic arm and the top coat as well. Here we see the spray up. We are doing the bottom of the tank. So we do the bottom and it's all coupled to the tank. It's a high productivity machine that is used for producing tanks. Here we have the releasing, the demolding operation, the releasing. Next. So I think we reduce the time. Time is reduced when we apply the chemical barrier as well. Well, as you may, use the machine without the robotic arm. The robotic arm has, of course, great advantages, but there's a cost to it. So you see the demolding operation on the video. Next. Well, that's a project that we developed. We didn't produce the part. We made the prototypes, the entire essays, and the entire study. The railroad dormant. Well, this is because of our railway engineer, our colleague here at the IBCon. So he always insisted on that, on working on this. So this wooden piece is no longer available. That's forbidden. It's forbidden to use wood in the railway road. In Brazil, we use the concrete elements, but it weighs 400 kilos. And this one, this piece here, weighs 30 kilos. It measures 2.60. It's the tie element in the railroad. Well, if you have a railway made of steel, you use 1,300 ties per kilometer, the track ties per kilometer. So you need to take that into account. There must be a high throughput in the production of the track ties. So we developed, this tie for the railroad. So this is the final development. It is a totally new process. It's unheard of. Nobody has ever used this process to produce such components. So we produce one tie every 5 minutes. Monthly production amounts to 32,000 track tie elements to meet the needs of the railroads. Well, here in Brazil, as we don't use that much trains and concrete, with the high-speed trains and with the vibration, there's much noise, and it also crumbles apart over time. But here in Brazil, the passenger railway transportation is not widely available. We have no high-speed trains available in Brazil yet. So our technology has been saved for a later time. But it is a solution even for other countries that have, high-speed trains in their railroads. As you will see here, the cost of production. Let's go to the next slide. So our production process is a process whereby you have a high cost of raw materials. The production cost, though, is low. Technology cost is low as well. So it's high throughput, and it's just like the other scheme that we saw. So the important thing is developing the appropriate process for such production. And fortunately, we have great experience on that. Next. Natural gas pressure vessel. Well, we began working on this. Well, in the beginning, there was this company that was connected to Transpetro, and they were the ones who requested this development, and so we did. Here we have the internal part that is roto-molded with a thermoplastic. We have the metal parts, the metal inserts. So in the head, you have the metal inserts. And here, this is where we place the valves and everything else, the other elements. And we developed this project entirely in carbon fibers and aramide. Aramide was used in the cylindrical part. Next. Very well. We reached the conclusion. Can you further enlarge the image so that we can see the table? So here we compared with a steel product. So we made it for trucks, two different sizes, for passenger vehicles, for trucks, and for buses. So the weight, when it's empty and when it's made of composite, it was 22 kilos for the passenger vehicles. And steel, it would be like 42 kilos. Well, this is like 20 years ago. We shouldn't use such amounts anymore. So that was the cost for passenger vehicles. When you made it with a composites or a steel, composite would eventually be more expensive. But for trucks, the volume is higher. As incredible as it may seem, well, composite would weigh, 71 kilos and steel 123 kilos. And in the case of trucks, composites were a bit less expensive than steel components because of the high throughput. All these products, the poles, the ties, all of that has a break-even point. That is a minimum productivity that must be ensured so that the cost targets may be met. Next. Here we have the production per se. So simultaneously we can manufacture 2 or 4 pressure vessels to meet the market demands. Next. This is what we saw before, the raw material costs. That's the strategy that we have for marketing and for being able to have access to the market. So you have high throughput and low labor cost. And this enables us to meet the market demands. Next. This is interesting as well. That's the gutter cap. It's made of cast iron, and the water supply company in the state of São Paulo has more than 2,000 of those. So the drainage system manhole cover, this is what this is. In this case, we also made an assessment, and we reached this conclusion. So in this case, we had to develop a process that was totally different, right? So we began using a certain compound for molding. So we had fiber with resin being used, and it's hot pressed. It's hot pressed. And we made this because there's 30 ton. This is what we used in the testing. We made the prototype, and the prototype was approved. But the productivity, in order to be competitive, just like the steel product, well, as I said, productivity has to be 10,000 covers a month. And we reached a price. We reached a price that is similar to that of cast iron. I said steel, but it's cast iron, he says. But then we were finally in touch with the clients, and then we asked them, what if there is a price rise? And then the clients, they really take into account price. It's all about price. So the investors were somewhat fearful. because we talked to cast iron cover manufacturers, and they were selling at very high prices. They had much fat on that price. So if we were to launch, they would lower their price drastically, and the investment for producing such pieces is very high investment. These are high capacity pieces, you know. So here in Brazil, we did not produce such covers for the drain manhole. But in the United States, for example, they use this kind of cover made of a composite, and they do, you know, red for the fire department, green when it's the city hall administration. But here in Brazil, it's a project that is saved. We do have technology available. We have stored it away. When interest arises, then perhaps we can serve them. Next, that's a very interesting project. It's the last project that we did. That's a reservoir, a water reservoir. In this case, you have a 55 kilo weight and it's 6 meter high. In order to pour water with an outlet pressure of 6 meter of water column, there must be the infrastructure. So it's a popular housing. So they would, you know, manufacture it in concrete, and then they would use a regular water reservoir. And then when they saw this project of ours, they saw this in one of our clients. And the idea of Aqualitro, as we call it, is to sell the water reservoir in retail shops. So you go to the construction outlets, so you buy it and you install it easily. So the piping is pre-installed. All you have to do is connect the water supply input and the water outlet connection, and that's it. So we developed this production process for them, whereby you can sell this at very low prices, highly competitive prices. It's much less expensive than, you know, building a slab on your house, reinforcing the roofing of the house to be able to install a water reservoir. This is different. You place it at a higher place, at a higher height, and it's all said and done. So after this development, we have a certain production scale. And now we are about to organize a plant to produce 2,300 of these a month. This product was patented all around the world, so there'll be high volume of production of this project. Next. Well, Aqualitro is part of our scheme. It's part of the system. You know, you have a high cost of raw materials, labor.
The production or manufacturing system is fully automated. We've made the prototypes. They are already accredited according to ABNT, the Brazilian technical norms. It's currently undergoing the final stage of tests at Sabesp, the sanitation company for the state of São Paulo, and other companies as well are testing it. Throughput is still low because the plant is not in full operations yet. In this slide, we see how easy it is to install this in the field. This is a video. And here you can see the manufacturing of the first prototype with a roving method, filament winding. This is a 4-program access machine. It's quite a complex winding process. You have the conical structure or part of the structure, then you have the cylinder part of the structure. So it's quite a complex process. Each machine can make 2 of those at a time, just like with the posts. Our plant is fully automated. Well, we have shown you our expertise in process development, and this is what we love to do when clients bring us problems to be solved. And we develop products and processes in order to help the market. We have developed a full program of structural calculation that is based on all the regulations, norms, and security requirements. This program already calculates mechanic properties, thicknesses. It takes into account all necessary aspects. So this program encompasses the whole production technology. It can be used for tanks, tubes, posts. So the technology is fully embedded in the program. It's very easy to use. With about 4 or 5 hours of training, and we can provide remote training, operators can use the program. And in just 5 minutes, you can meet the needs of customers. You have the price, costs, and delivery dates. And we generate reports for clients. We look at the quality of raw material, and we have the calculation memory as well. We have lost connection with the speaker. Unfortunately, we have lost connection with Mr. Francisco. In the meantime, I'm going to give you some housekeeping notes. It happens on remote events, right? We are always subject to these problems. So today, in the Africa webinar, this is the last panel in the Africa webinar. So this was a master class in composites, a lot about polyurethane engineering plastics. It has all been recorded and will be made available to everyone next week in both languages, Portuguese and English, so if you want to watch it again or if you want to show this to other colleagues. So we have Global Composites, Solvay, Amino, Brenntag, and IBCOM. These were the morning presentations. At 2 p.m. Brazil time, we will begin with the Latin America seminar. We will have interpretation between Portuguese and Spanish. And we will have presentations from Texiglass, Alan Harper, Poglass, Cortifiber, Solvay, Amino, and Brenntag. We'll be presenting this afternoon. So a wide array of topics and materials will be covered in these presentations. I am just checking here if we have Mr. Francisco back with us. I think we do. Let's just check. And he's about to finish his presentation. Hello, Mr. Francisco. We lost you for a minute. We now can hear you. Yes. You were speaking about the program, right? And the calculation memory. Yes, I was just about to finalize. We were speaking. My apologies. We have a shortage of power here where I live, and that's why I lost connection. I do have a no break, but unfortunately the internet services carrier, they don't have a no break machine. In any case, we perform structural on-demand or tailor-made structural calculations. We have an amazing team working on it, and we can develop also turnkey projects. Next slide, please. I've mentioned equipment already. We have this partnership with Olmec, and we produce machinery, specific equipment that is needed to work with composites, and we are constantly available for whatever needs you might have. And we also provide in-company training courses. These are courses based on Antonio Carvalho's books about properties, structural calculation, and durability of composites. These are the in-company costs we have available. We also have the bibliography, or the list of books, Mr. Antonio Carvalho's books. He's an IBCOM member. There's one on the durability of composites, tank calculation, and other books that are about to be published. And we are collaborating and providing the bibliography. So I thank you very much for your attention, and we remain available should you need any additional information. We are here for whatever you might need. Thank you very much for this opportunity, and congratulations, Simone, on another amazing event. We thank you, Mr. Francisco. What an interesting presentation, so many interesting information. And you mentioned that you are waiting for a process regarding track ties. I hope you let us know about this process at FEPLAR. I'm going to try to find out what this is about. I can tell you part of the secret, actually. Well, I can tell you what this is about. It's composite based on thermoplastic. But it's going to be groundbreaking for a large production volume. Okay, so at FEPLAR we will have more information. Mr. Francisco, thank you so much. IBCOM will have a booth at FEPLAR. They have the IBCOM forum about durability, as he has mentioned. It's free of charge, the admission both to the fair as well as to the presentations. Mr. Francisco, thank you once again very much. Thank you, and I wish you all a great afternoon. So everyone, thank you very much for joining this morning. I hope to see you this afternoon. We will resume at 2 p.m. Brazil time. And if you don't join us today anymore, I hope to see you at FEPLAR and FEPUR in August on São Paulo Expo here in São Paulo, Brazil. Thank you very much, and see you next time.